Okay, example 2 in section 5.4. The sequence a1, a2, a3, so on is defined recursively as follows. The first term a1 is 1, the second term a2 is 3, and for the future terms, they are defined recursively using that what we call recursive formula. So this is what we call in this section recursive formula. Okay, great. For any integer greater than 3 or equal to 3. So suppose we want to prove that an is odd for all integers n greater than or equal to 1. So this is going to be a proof that relies again on strong induction. So proof by strong induction. And we're going to start by saying let the n be greater than or equal to 1 because of this, but first let's assume that it's an integer to begin with and make it greater than or equal to 1. Okay, great. So the base case. So we did a problem similar to this one in section 5.3, and that recursive formula had only one term. This one here has two terms. So the future ak is defined in terms of ak minus 2 and ak minus 1. So what we're going to do is we're going to have to test out multiple base cases. In this case, we're going to have to start with n equal to 1 because that's the first number in my domain, but we may have to do additional n equal to 2, n equal to 3, and so on and so forth. How many do you need to know? Here's how you figure that out. So if you kind of think about how far apart is k from k minus 2, it's 2 steps away. How many steps is k away from k minus 1? It's 1 step away. The greater one of those numbers is 2. That's why we're going to be needing to do two base cases, n1 and n2. So this is kind of important, keep that in mind as you work on these kind of problems in section 5.4. So now that we have determined how many base cases we're going to do, let's go ahead and investigate. So first of all, I'm going to grab the a1 and it's a 1. What do I have to know? I have to check, is it actually odd? So odd, which is great. So the theorem is true so far. What about a2? Well, a2 is supposedly 3. They told me that information, and I need to check, is it actually odd? And yes, it is odd, so the theorem is still going to be true. And so far, the base cases look like they're amazing, and we're ready to the inductive hypothesis. So let's take a look at how we do that. So inductive hypothesis, what we're going to do is we're going to say, suppose that the theorem is actually true for the following. So suppose that an is odd, that's the theorem, for all the integers, for any integer n that goes from 1 to some random number k, where k is some integer. So basically we're saying, suppose the first k integers are basically odd, okay? And we're talking about basically the AKs that you get from this recursive formula. We would like to show that the AK plus 1 term in the sequence is also odd. That's our goal. And to do this, we are going to basically set it up the same way we did in previous sections. We're going to look at the recursive formula and see what we can get this. So we're going to say we know that AK is AK minus 2 plus 2 AK minus 1s. Okay, but we're interested in knowing what's going on with AK plus 1. So then let's replace all the K's in this formula with K plus 1s. So that would give us AK plus 1 equal to AK minus 1 plus 2 AKs. But keep in mind that we assume that every number 1 through k, every index gives us a term that is odd. So what does that mean? Since k minus 1 and k are less than or equal to the k, they are the index of some term, their terms are going to be odd. Then AK minus 1 and AK are odd. How do we know this? We know this by the inductive hypothesis step. So, well, i.e., there exists, let's say, m and n that are integers such that ak minus 1 is equal to 2m plus 1 and ak is equal to 2n plus 1. This is by definition of odd. And so we can now go back and plug everything into the formula that we have. So let's see. So ak plus 1 will become 2m plus 1 because that's the ak minus 1. Okay, so let me use some colors so you can see it. This right here is going in place of the ak minus 1. So that's why I'm getting the 2m plus 1. And also, similarly, we get 2 times the 2n plus 1 because of the fact that ak is 2n plus 1. And so the substitution leads to that 2n plus 1. So this is now 2m plus 1 plus 4n plus 2, which can be written, if you want, as 2 times m plus 2n plus 1. So I'm factoring the 2 out of these 3 terms, and I'm kind of leaving the extra 1 on the outside. But keep in mind that m, n, and 2 and 1 are all integers, so the product and the sum of them is going to be integers. And this means ak plus 1, the term, is odd by definition. And that's what we set out to do. We wanted to prove that ak plus 1 is odd, so that means we are finished with this problem. Cutie.